My name is Owen Shea, and I'm the Weather and Climate Program Manager at the National Disaster Preparedness Training Center. Today we'll be discussing Unit 15, Fundamentals of Hazardous Weather. The objectives of this unit are to discuss the importance of weather, classify the different types of hazardous weather, and we'll also explain the causes and conditions associated with hazardous weather. We'll bring this home and describe the region-specific hazardous weather threats around the country and identify threats associated with each type of hazardous weather event. First of all, I'd like everyone to think about why weather matters. Have you had any weather experiences that have confirmed to you that weather is a very important problem to consider? Nationally speaking, weather matters because, on average, we have 641 fatalities across the United States per year. This is a 10-year average. And the U.S. economy is sensitive to weather variability up to about $500 billion per year, or 3.4% of our GDP, according to 2008 dollars. This excludes extreme events and climate change. So this is just the amount of the economy that's sensitive to the day-to-day changes in weather patterns. About 90% of presidential disaster declarations are related to hazardous weather. So within the realm of natural hazards, it's pretty clear that weather is a dominating problem. $3.8 trillion was the cost of natural disasters since 1980, according to the World Bank estimate. When we look at each year, in 2014, 13, 12, 2011, and going on back, we see that we've been dealing with many billion-dollar disasters across the United States. 2005, of course, stood out because that was our most active hurricane season on record to date. We had $187 billion due to Hurricanes Katrina, Rita, Wilma, and Dennis. And we all know about how that really shifted emergency management policy as well. In 2011, the big problem was actually tornadoes, even though on a yearly basis that's not the primary weather hazard. But because of the Joplin tornado and the outbreaks across the southeast United States, the Weather Ready Nation Initiative of the National Weather Service was founded because of those events, and it was a momentous shift in terms of the weather preparedness community as of that year. When we look at a graphical representation of billion-dollar weather and climate disasters, we see that a big part of the threats come to the coastal community. So we look at the states, everywhere from Texas to Virginia, particularly in the southeast, are very vulnerable to billion-dollar weather disasters, and I think that's pretty easy to see that this is part of the hurricane problem that our country faces. Which can bring heavy rain, flooding, storm surge issues, which we'll talk about in the following slides. When we look at weather fatalities across all the different hazards, we see that in the long term, in the 10 to 30 year average period, we see that heat and flooding, so water and extreme heat are the primary killers when it comes to weather hazards. However, in the year 2011, as mentioned before, what stood out was the amount of tornado activity that resulted in deaths. Unfortunately, we had a lot of killer tornadoes that year, and you see in this figure, we have 553 deaths recorded from that year, which is far greater than the average amount of tornado deaths on any given year. So what are the ingredients for weather? What makes weather such a violent part of the world of natural disasters, but also something we have to live with every day? It really depends on atmospheric composition, solar heating, the tilt of the Earth, differential heating between land and water. These are all conditions that play into how weather changes on a day-to-day basis. There are temperature differences leading to distributions of weather systems. So high and low pressure systems, as they move across the land and the oceans, cause changes in our wind patterns. There's a tendency for nature, when placed in an unstable state, to struggle to reach stability. So what that means is whenever things are out of balance in nature, the Earth will come up with a way to right that balance. And that correction process is a storm. That's why we get storms. And the sun, of course, drives the Earth's weather. So when we talk about the Earth's composition, we think of oxygen as the most important thing because that's what we breathe, but in reality, most of the air is made of nitrogen. And then oxygen follows from that in terms of percentage composition. And after that, a tiny sliver of the air consists of a lot of other gases. And not shown here is a very important gas, water vapor. It's a very, very small percentage, but the fact that we have water vapor in the air causes condensation. Condensation releases heat, and this process leads to storms, as we know it. Another condition, of course, is the Earth's tilt. Depending on where we fall relative to the equator, we get a different amount of sun, and that leads to temperature differences. And as the Earth revolves around the sun, that gives us the seasons, because sometimes the northern hemisphere will get more sun than the southern hemisphere, and vice versa, depending on the time of year. Differential heating between land and water is very important. For those who are from Florida, you're very familiar with this phenomenon, with the sea breezes that will occur during the day, because the sun heats the land, and as the land warms, the cool air will rush in to replace the rising warm air, and you create this circulation of air between the lake, or between the sea or the lake and the land. At night, the effect is opposite, where the land will cool quicker than the body of water, and so you get a land breeze, where the air blows away from land. This is important because anytime the air is horizontally moving and collides into surrounding air, you'll create showers and thunderstorms. And so, depending on where the breeze is blowing, you'll get different patterns of rain. The atmosphere needs to be unstable in order for a storm to develop because, again, remember, the storm is the atmosphere's way of correcting an imbalance. So what is an imbalance? If we look at a figure like this, which ball is stable? Ball number 1 is stable because if we were to move it, push it away, it'll oscillate and return to the valley. Ball number 2 is unstable because if you were to push it, it would accelerate away and would not come back. So an analogy to this in the atmosphere is the sun heating the ground, and as the ground warms, the layer of air right above it, it becomes warmer, and warm air wants to rise. So when that happens, it's trapped under a layer of cool air, and that becomes an unstable situation. When that boundary is broken, then the warm air will rise rapidly, and as it rises, it will condense, and the condensation releases latent heat, which then warms the air even more, and it keeps going. That usually develops into a thunderstorm if the conditions are right. There are other types of instabilities. You have horizontal instability, where in the cold winter, oftentimes you'll have a cold front diving through the southern plains, and as it reaches the warm Gulf of Mexico, the boundary will sit there. And after a few days, when conditions are right, the Earth will try to mix the cold and warm air. This is the birth of a mid-latitude cyclone. And as the mid-latitude cyclone develops off the coast of Texas, essentially what it does is it rotates counterclockwise, and so the cold air starts diving southward, the warm air moves eastward and northward, and this gives us our changing weather day to day. Extreme cases will give us storms such as nor'easters that we see in the winter oftentimes on the East Coast. All of this plays into the global atmospheric circulation. As we said already several times, the Earth has a way to try to balance itself. And one way it does that is through global circulations, where as the sun heats the equator warmer and quicker than the polar regions, you have rising air near the equator. And as the air rushes in to fill its spot, those are the trade winds. So that's why just off of the equator to the north and south, we have easterly trade winds. As the air rises and descends around 30 degrees north and south, that's where we find the world's deserts. So there is a pattern here in terms of the global climate zones. For the rest of this course, we really want to establish different definitions for some of the jargon and terminology that we'll be using. When we talk about weather, we're discussing short-term variations of the Earth's atmosphere. Climate is the long-term average of that. So you can think of it as a long-term variation of weather in the Earth's system. How about severe weather? Severe weather is actually a really technical definition. According to the National Weather Service, severe weather includes thunderstorms and related weather, such as tornado, lightning, hail, and wind. However, severe thunderstorms have a specific definition, which we'll get into later. That's the same as a severe thunderstorm warning in terms of criteria. Extreme weather is a term that's used to describe events that are extreme to a particular location. So what we mean by that is 30-degree wind chill would be pretty extreme for South Florida. And so that would be of concern to the population. However, 30-degree wind chill for New York would just be another day anytime in the fall or early winter. And so extreme weather depends on location. So we have to make sure we know what we're referring to when we're discussing that term. There is a method to the madness. When we look at the weather and climate spectrum, we see that the larger the weather system, the longer it lasts, or the longer the duration or the cycle. The smaller the event, oftentimes the shorter amount of time it lasts. So on one extreme, we see tornadoes, where we're dealing with something less than a mile across usually, and lasts only for a few minutes. Whereas on the other extreme, we have climate change. It's a global phenomenon. Somewhere in the middle, we see tropical cyclones, mid-latitude cyclones, which then bring us heat waves, cold waves. In the winter, we can have ice storms and blizzards. Lake effect snow can come behind a passing cold front. So there is a method to the madness. If you notice, there's a pattern, right? And so these can cause cascading events or cascading hazards, similar to the term that's used in emergency management. With weather, we have a similar thing, where a mid-latitude cyclone can cause virtually everything else down the line. Tropical cyclones can also contribute various different hazards as well. When we look at this same chart, but using an inverse pyramid, we see that the bigger event on top of everything that affects everything down the line is climate change. Now, climate change can be a result of both natural forcing and anthropogenic forcing, or human forcings, the amount of which depends on the situation. And there's a lot of research going into exactly how much is caused by humans and how much is natural. But the fact is, both of them are part of the larger picture. Now, under climate change, you can also consider oscillations, and these are essentially the seasonal, the annual, and the decadal changes in the atmosphere that are natural, that have been going on from the beginning of time as we know it on Earth. These include El Nino, La Nina, the Mad and Julian oscillation, which is a cluster of thunderstorms that will occur over the Indian Ocean and move eastward. And as it does so, it changes global circulation, and it can even affect the weather in the United States. Monsoons and droughts can all be considered part of these oscillations. Farther down the line, we have synoptic storms. These are storms that occur kind of on the multi-state to half a country scale, and these are the storms that we experience on a daily basis. And then we, of course, have local impacts. This is what matters to a local community. And as emergency managers, our primary concern falls on the bottom half of this pyramid, even though what occurs above does affect it to a certain extent. So when we look at cascading events, this is one way to see how all the hazards relate to two primary types of cyclones, and these are the ones that we'll focus a lot of our discussions on. Tropical cyclone would include hurricanes, typhoons, things of that nature. It's essentially a rotating storm that is born in tropical oceans. Those can lead to damaging wind and tornadoes, in fact, and also provide a lot of heavy rain and storm surge. And this can contribute to coastal flooding as well as inland flooding, such as flash flooding and river flooding. Mid-latitude cyclones are different. Rather than being born in the tropics, they thrive off of horizontal temperature differences, such as that figure we saw showing the cold air over Texas and the warm air over the Gulf of Mexico. Mid-latitude cyclones are often usually divided into two sections, just by definition. You have the cold sector and the warm sector. This temperature difference is more extreme in some cases and less extreme in other cases, but you'll always have a cold front and a warm front, by definition. On the cold sector, you'll see blizzards, oftentimes ice storms. Lake effect snow can come behind the westerly winds or from behind the cold front, depending on the orientation of the lake. The warm sector, you'll have thunderstorms and persistent rain. Thunderstorms, of course, can lead to lightning, which then can cause wildfires. They can also cause flash flooding, which can lead to landslides, and of course all the other hazards such as hail, rain, causing river flooding, and then wind. Wind would include tornadoes, derechos, which are straight-line windstorms, and microbursts. So what are mid-latitude cyclones? We mentioned their formation earlier, but just as a matter of comparison to hurricanes, they're cold core, low-pressure systems that actually drive the day-to-day weather across the United States. On any given day, you'll have a mid-latitude cyclone somewhere near or in the United States. They come from horizontal temperature gradients, and they're pretty large. They're much larger than a typical tropical cyclone. And so all the fronts that are associated with the mid-latitude cyclone can lead to the changes in day-to-day weather. And the strongest winds are in the upper troposphere. So what that means is the jet stream drives a lot of the mid-latitude cyclones, and that's at the altitude of approximately where commercial aircraft will be flying. These serve as parent thunderstorms to a lot of other types of hazardous weather, such as thunderstorms. This is a figure we saw earlier, but just to illustrate again, we have cold front moving to the south, warm front moving to the north, both of them circulating around a low-pressure center, and that would be the mid-latitude cyclone. The mid-latitude cyclone will die once the temperature contrast has been washed out, because it will have accomplished its mission at that point. Here's another view, three-dimensionally. You see that the cold air will wedge under the warm air as the cyclone rotates around itself, and by the time the air fully mixes, then the mission is complete. The instability is diffused at that point. And again, storms exist to balance out instabilities in the atmosphere. So once that instability is gone, there's no need for the storm anymore. So what are some typical mid-latitude cyclone tracks? A really common one is formation just east of the Rocky Mountains, and it'll slide across the central part of the United States. Those storms in the springtime often give us the severe weather outbreaks that we see in the southern plains and across the southeast. In the wintertime, we deal often with what are called Alberta clippers. That will be a very fast-moving mid-latitude cyclone forming near Alberta, Canada, and sliding eastward across the northern United States, giving a quick burst of snow that will last really no more than a day or a few hours. In the winter, oftentimes, the extreme temperature contrast between the coast of Texas and the Gulf of Mexico will also drive the formation of a mid-latitude cyclone, which as it rides up the east coast will become a nor'easter for the people in the Northeast and New England. An extreme example of a mid-latitude cyclone is the historic storm that occurred on October 26, 2010. As you can see, this is an extremely large circulation that is centered over the Great Lakes, but the cold front drags all the way south in the Gulf of Mexico. So a mid-latitude cyclone can be as large as half the country. Where on the backside, the cold sector, you have blizzards, and on the warm side, ahead of the cold front, there's severe thunderstorms and tornadoes. If we were to change the scale of the maps here so that they match each other, you see that in the case of the landfall of Hurricane Katrina, the storm was actually much smaller than a typical or a significant mid-latitude cyclone. And so the effects are different. With a mid-latitude cyclone, the effects are much broader. It impacts a big portion of the country, whereas with a tropical cyclone making landfall, such as Hurricane Katrina, yes, it was a much more intense storm, but it's much more isolated and focused on a certain part of the coastline. So, what are tropical cyclones? They're warm core, which means they don't have warm fronts or cold fronts. They derive energy from the moisture rather than from horizontal temperature differences. The strongest winds are near the surface, which is why in a case of a hurricane, the impacts are much greater than a mid-latitude cyclone. But the primary threat is the coastal areas. Mid-latitude cyclones, because they thrive off of temperature differences, they don't care if they're over land or water. They can move around freely. Whereas with a tropical cyclone, they feed off of the moisture of the ocean. So the moment they make landfall, they will start to die. Tropical cyclones are, of course, then confined to the oceans, but whenever they make landfall and before they weaken, that window of time causes the most destruction. Looking at it globally, we see tropical cyclones occurring in all of these locations. We get the most press in the United States from hurricanes that develop over the Atlantic, but as you notice in the tropical cyclone track shown here, that the western North Pacific is actually far more active. The eastern North Pacific is also more active than the Atlantic. The waters are warmer. The conditions are often more favorable for the development of tropical cyclones. Southern Hemisphere, some of the most devastating ones have occurred down there too, such as the cyclone that hit Vanuatu last year. We have storms that will occur in these regions. But if you notice, there's a gap right over the equator. This is because relative to the Earth, there's not a lot of rotation being imparted by the rotation of the Earth at that location. So you have to be far enough away from the equator so that air wants to spin. When we look at the United States, we see that we have a hurricane problem. Just looking at this figure of all the tracks since 1851. The west coast of the United States hasn't really had much in the way of tropical cyclone activity. San Diego has had some near encounters, but nothing as destructive as what we see on the Gulf Coast and on the eastern seaboard, where we are right in the path of hurricanes and tropical storms that would form in the Atlantic. Tropical cyclones are classified according to maximum sustained 1-minute average wind speed at the surface. These are estimates derived from either aircraft reconnaissance or satellite estimates. And what we see is winds that are sustained at 39 miles per hour or less than 39 miles per hour is considered tropical depression. Tropical storms are winds between 39 and 73 miles per hour. And hurricanes are when winds are 74 miles per hour sustained or greater. You may wonder why the numbers are precise to the single digit. The estimates are actually never that precise. These are simply converted from knots, because by tradition, knots is the unit of measurement for wind speed in meteorology, to match aviation and maritime concerns. Major hurricane would be Category 3 or higher, and when we talk about tropical cyclones, they're hurricanes in the Atlantic, and then typhoons in the Pacific. The term hurricane is also used for the North Central and Northeast Pacific, but west of the dateline it becomes a typhoon. Cyclone is the generic term used elsewhere. The Saffir-Simpson hurricane wind scale ranges from 1 to 5. This is only used by the United States, so this is only for the Atlantic, the Eastern North Pacific, and the North Central Pacific storms. So for hurricanes that affect Hawaii and also the eastern seaboard, this is the scale that we use. Major hurricane, again, is Category 3 and higher. So what does a tropical cyclone look like? If we were to draw a schematic and then cut it in half, we see that a tropical cyclone consists of a spiral of swirling winds feeding off of the warm, moist ocean water. And as it spirals in and rises, the air condenses into bands of thunderstorms. And as the air leaves the top of the cyclone, it'll actually rotate clockwise. It'll rotate in the opposite direction as the exhaust mechanism of a cyclone. Thankfully, in terms of planning purposes, these tropical cyclones follow seasonal cycles. And in the Atlantic, we see that the peak occurs somewhere near Labor Day. So every year during Labor Day, there's often at least one storm in the ocean basin. It tails off on both sides, and so the official hurricane season starts from June 1st and ends on November 30th. But of course, we've seen storms occur beyond that time period. It's just that the official season is during those 6 months. By far, the most dangerous part of a tropical cyclone in terms of hazard is storm surge. And storm surge comes from, essentially, without going into the physical details, comes from the piling up and the pushing of the wind over the surface of the ocean water. And as the cyclone nears shore, all of that air pushes the water ahead of the right front quadrant of the storm is the most dangerous side, and that's where a lot of the water will pile up, and it's a gradual inundation with waves on top of the surge, eating away at a lot of the coastline as well as the structures along the coast. And so it's a very dangerous phenomenon because it's a gradual. It doesn't come in as one large wave. It's a gradual rise in water as the storm persists. But on top of that, you have wave action to be concerned of, as well as tides. And so depending on the timing of the landfall, the effect of the total water rise will be greater or less, depending on the situation. Let's go smaller scale now. So when we talk about thunderstorms, this is something we're all familiar with, no matter what part of the country we live in. They can develop anywhere. They may be associated with the frontal zones in a mid-latitude cyclone, or they could exist on their own. Just as long as you have enough instability, sun heats the ground warm enough, such as in a summer thunderstorm scenario, then you can get a few minutes of heavy rain coming out of a thunderstorm. They can also lead to tornadoes, wind, hail, lightning, flash floods. Really, the conditions that causes a thunderstorm to develop consist of lift, instability, moisture, and wind shear. All you need is lift, instability, and moisture for the development of a daily thunderstorm over the summer, but you need wind shear in order for severe thunderstorms. And this is because you want the part of the storm that's raining to be separate from the part of the storm that's feeding in the warm, moist air. And you do that by tilting the storm through the wind shear mechanism. Thunderstorms are distributed across the country. Every state gets them. However, if you notice on this map, Florida is the lightning capital of the world. And we see, lightning capital of the country specifically. And you see that most of the thunderstorms occur there. And that's because of the sea breeze boundaries that we discussed earlier. There's also quite a few thunderstorms that will form off of the Rocky Mountains. And so we see another maximum in the Colorado and New Mexico area. As a thunderstorm develops and the air condenses, it eventually begins to rain. As we mentioned earlier, the rain typically falls on one side of the storm, depending on how much the storm is tilted, and that depends on wind shear. But eventually the storm will choke itself off by raining out. And when the rain hits the warm air coming in, it'll actually cool the area near the thunderstorm, and that'll ultimately kill off the thunderstorm. However, there are some storms that maintain itself for many, many hours, and these are called supercell thunderstorms. And these exist with enough wind shear and enough instability that it's able to ingest a circulation that will develop inside the mesocyclone or the rotating updraft. So this is essentially a rotating thunderstorm. And these are the storms that create our most devastating tornadoes. Tornadoes are, of course, often, not always, a funnel cloud-shaped rotating vortex that will touch the ground. However, some of the most devastating tornadoes occur in areas where it's difficult to identify the shape of the tornado, such as in the southeast, where the tornado could be wrapped in rain more frequently or obscured by hills and trees. If you look at these two photos, we see that oftentimes in public safety manuals, we see a tornado being this really nicely shaped funnel touching the ground. But tornadoes can be also a really, really large vortex that just looks like a wall dragging the ground. And the figure below shows that. And so from a public awareness and safety perspective, a non-traditionally shaped tornado could often be more dangerous because the public simply does not understand that that's actually a tornado that's on the ground. When we look at global tornado distribution, we see that the United States is one of the areas that gets a lot of tornadoes. Europe also can get some, as well as areas along warm tropical ocean waters, but they have to be on land because the dynamics of the situation warrant more tornadoes over land than over water. If you look at the distribution, you also see that they occur over the mid-latitude regions. And this is because tornadoes often occur in high wind shear environments, and high wind shear environments come from areas with jet streams. And so mid-latitude cyclone territory is also shared with tornadoes. When we look into the United States, we see that there's a maximum of a tornado development right over the central part of the country. And this is a very interesting phenomenon because notice how just east of the Rocky Mountains we see more tornado occurrence, and this is tied to the mid-latitude cyclone tracks we discussed earlier. But that doesn't mean that if you're in Nevada or you're in California, you won't get tornadoes. You still get them. Tornadoes occur in all 50 states. They're just less frequent. And so from a public safety perspective, as emergency managers, we have to be concerned about the level of awareness and preparedness in areas that can get tornadoes, but maybe not often enough for people to really care about them. And so, for example, in central Oklahoma, given how frequent tornadoes are there, there's been very good public awareness campaigns on this for years. And so everyone who lives in central Oklahoma knows what a tornado is, knows what a supercell thunderstorm is, and knows ways to prepare. Whereas areas such as New York may not necessarily have as much preparedness because a vast majority of the public think that they don't get tornadoes. And this is something that we see when we deliver training courses in that area. But they still get them, and they can get some pretty significant tornadoes as well. They're far more rare, but they can still occur. So the frequency of tornadoes can be tied to the seasonal changes. And so when we think about a tornado season, oftentimes we think April, May, June time period, so the spring. However, this depends on where you are. If you are farther south, if you live in the southeast, then tornado season is actually in the wintertime. If you live in the Dakotas or if you live up in the northeast, tornado season is actually more toward the summer, the early summer. And this is simply because of the cycle of the jet stream. Tornadoes are a really unfortunate hazard because in addition to their violent nature, they also occur right at evening rush hour, more often than not, or just after the sun sets, due to various dynamical reasons associated with these storms. That's when peak heating occurs from the afternoon sun. That's also when the wind shear can also maximize, given the conditions right at sunset. The enhanced Fujita scale was developed to try to rate the impact of tornadoes. And this is under our thunderstorm section, but this scale itself is referring to tornadoes. The scale is from 0 to 5. The enhanced Fujita scale is an updated version of the old Fujita scale. And what you see here is wind estimates based on damage. So the damage that's been done after a tornado occurs. There's no way for us to, in real time, determine the intensity of a tornado. We do not have a technology for that. Unless you have a mobile Doppler weather radar sitting in front of a tornado at the time of its occurrence, there's no way for us to estimate intensity. Take-home message from this scale is, if you notice on the right column, the percentage of U.S. tornadoes that fall under each of these categories. Notice how the most intense tornadoes, EF4 and 5, comprise of less than 1% of all occurrences. And what's important about this is the 4 and 5s get the most news media and press attention directed at them, but they are actually very, very infrequent relative to other types of tornadoes. So what does this mean? Well, that means that we can prepare effectively using just common sense measures. Staying on an interior room with the lowest floor away from windows if you don't have a basement. Being in an interior bathroom where the room is surrounded by piping can be a sturdy enough shelter for the vast majority of tornadoes. When we prepare for tornadoes, oftentimes we think of what's in the movies, what's in the media, and so we're preparing for an EF4 or 5, which is great, but occasionally, and it's been documented to occur in recent years, there's been panic that can be induced, where people feel like they have to drive away if they don't have a basement, otherwise they won't survive the storm. That is not the case, as you can see here. The vast majority of tornadoes will be survivable using common sense measures. Another type of thunderstorm hazard is the microburst. The microbursts are essentially a rapidly descending area of air. As it hits the ground, it'll spread out, and this causes a gust front circulation. And this is particularly hazardous to aviation, particularly when a commercial airliner is coming in on approach. Reaching the beginning part of microburst, they will feel a headwind, and as that happens, the aircraft will lift above the glide slope, and so the pilot's initial response instinctively is to cut the throttle to get back onto the glide slope. When that happens and the aircraft reaches the other side of the microburst, all of a sudden there's a tailwind and the aircraft loses lift, and in the past have slammed into the ground. A lot of casualties have come from this. However, the good news is we understand microbursts very well now, and in the past decade, we've made significant advances in terms of early warning of microbursts and wind shear to pilots that are flying. So this is a very good example of a hazard that through technological advances we've significantly reduced our risk to. Hail is another problem within thunderstorms. Thankfully, these are not very life-threatening. However, they are a significant threat to property. So we can get a lot of vehicle damage. They're a big threat to agriculture because they can destroy a lot of crops. When you have golf ball size or baseball size hail falling from the sky in vast quantities, that is a significant concern. And hail has caused a lot of damage to produce. Lightning is, of course, another concern intended with every thunderstorm. Lightning can be cloud to cloud, such as what you see on the right side of this figure, or cloud to ground. Those are the most dangerous because they're hitting objects on the surface. They can hit people, of course, and so lightning is a big killer within all the different weather hazards. But staying indoors away from windows is enough to shelter from lightning. Sheltering within a car is also relatively good compared to standing outside, because the car acts as a frame where lightning can go to the ground through the surrounding metal. Space weather is something that we talk about occasionally. This doesn't get a lot of attention among the general public, but it's a huge concern. to those in the telecommunications field as well as in the energy sector. This is because geomagnetic storms can emanate from solar flares in the sun, and as they interact with the Earth's magnetic field, we can have certain situations arise, such as satellite communications can go down. The electric grid can also go down. So this is an area of increasing study. We have the Space Weather Prediction Center in Boulder, Colorado, that's run by NOAA, and they focus on watching these events. And so we do have a system in place to be able to forecast and get a good observation of these events, but they're not really in the public concern. But in terms of our 21st century progress entering into more and more deeply into telecommunications type environments, we are becoming increasingly vulnerable to space weather as time goes on. And to conclude this unit, we'd like to have everyone spend a few minutes thinking about your weather experiences, what you've gone through. Do you have any lessons learned from an event that may have impacted your organization or your constituents? And with that, to conclude, I'd like to return to this image again as a tying theme of this whole course, and that is, there is a method to the madness of weather disasters, that they are organized in a certain way. And in this module, we hit on a lot of different topics, from tropical cyclones to mid-latitude cyclones and all the cascading hazards that occur from them, such as thunderstorms, tornadoes, etc.